Hi, my name is Tamir Desai, and in this video I'm going to teach you how to predict the product of a base-catalyzed keto-enol tautomerization.
Keto-Enol tautomerization requires a catalyst to speed the reaction up. The catalyst can be an acid or a base, and the mechanisms of both are similar. In order for a tautomerization reaction, we need a keto group. Let's use acetone, a symmetrical ketone for this example. As we learned earlier, we can predict the enol because we know it's an isomer differing only in the placement of a double bond and a hydrogen. The enol would look like this. Notice the double bond has shifted from the carbon-oxygen to a carbon-carbon, and one of the hydrogens on the keto is now bonded to the oxygen, creating an alcohol. The shift from a keto to an enol does not happen without an intermediary step though. So the first step is the keto reacting with a base. We'll use hydroxide, which is a strong base. The base will deprotonate a hydrogen on the alpha carbon, like this, creating a cascade of electron movement that shifts electrons between these carbons, and finally shifting the pi electrons on the carbonyl up to the oxygen. The resulting molecule, an enolate, now contains a carbon-carbon double bond and a negatively charged oxygen. Recall that catalysts are not consumed in a reaction. We started with the base, represented by OH negative, that deprotonated the keto, so it's now a water molecule. The negatively charged oxygen will deprotonate the base by attacking the hydrogen, which will shift the electrons to the base, which regenerates the catalyst. What we're left with is our enol. But what happens if we don't have a symmetrical ketone? For example, if our ketone looks like this. This could create two potential enolates, a thermodynamic product resulting in an enolate that looks like this, or a kinetic product where the enolate looks like this. Notice the double bond is the only placement that differs between the thermodynamic product and the kinetic, and certain conditions favor one product over another. The thermodynamic product results in a bond at the more substituted carbon, so this enolate is the thermodynamic product. The double bond at the more substituted carbon allows for the negative charge to be better distributed, leading to a more stable enolate. Temperature is the primary factor in determining the product, and the thermodynamic product is favored in high temperature conditions. Of course, this will vary by molecule, but anything greater than 0 degrees Celsius will form the top product. Additionally, smaller, weaker bases, like ammonia, will favor the more substituted carbon. In contrast, the double bond is formed at the less substituted carbon in the kinetic product, resulting in the bottom enolate. The less substituted carbon is not able to share the negative charge as well as the more substituted carbon, which means the enolate is less stable. Again, temperature is the first thing we look at when determining the product, and anything below negative 78 degrees Celsius will favor the kinetic product. But the base also has a role when the temperature is neither high or low. Strong bases, like LDA and KH, will favor the kinetic product. Let's apply this information to a question. Given asymmetrical ketones with unequal hydrogens on the alpha carbon, we're asked to predict the enolate that is more likely to be formed. Remember that the thermodynamic product is formed at high temperatures and favored with small, weaker bases like ammonia, and the kinetic product is formed at low temperatures and favored with strong bases like LDA and KH. Starting with A, the most acidic hydrogen is here, meaning it will be the one to get deprotonated. So the question is, will the double bond form here or here? Notice that we are not given temperature, but we do see a small weak base in the form of ammonia. Therefore, this will form slowly into the thermodynamic product, where the double bond ends up on the side with more carbons. Moving on to B, we need to determine if the double bond will form here or here. The temperature would not be considered low or high since it's neither less than negative 78 or more than 0 degrees Celsius, so we can't be sure which product will form with this information. LDA indicates a strong base though, so this should form the less stable kinetic product with a double bond on the less substituted carbon. C is identical to the ketone we saw in B and utilizes the same strong base, so we'd expect to see the same product. This time, the temperature is different though. 25 degrees Celsius is considered a high temperature, and this takes priority over the strength of the base, so this will form the thermodynamic product, with the double bond on the more substituted carbon. Lastly, D has two hydrogens that can be deprotonated, one here, which would lead to a double bond here on the more substituted carbon, and one here, resulting in a double bond on the less substituted carbon. We aren't given a temperature, but we do see a base. KH is a strong base, so we should see the formation of the kinetic product, which results in the following enolate on the less substituted carbon. That covers the base catalyzed keto-enol tautomerization. So not only should you feel comfortable with drawing the mechanism, but also predicting the product that will be favored in a reaction.